За сайн байцгаана уу? Эрхэм мөндөд зочид төлөөлөгчид, нийт хуралд оролцогчид та бүхэнд энэ өглөөний мэндийг дэвшүүлье. Good morning, distinguished guests, delegates, and ladies and gentlemen. Well, my presentation is entitled Environmental Studies of Mongolia Using Advanced Spatial Techniques. And within the framework of this topic, at the beginning, I'll give you a brief introduction, and then I will talk about 4 different case studies, namely forest change study using multi-temporal Landsat and GIS data, pasture land change study using optical and SAR images, analysis of environmental conditions using multi-temporal interferometric SAR images, global environmental monitoring using moderate resolution optical remote sensing images, and then I will conclude my presentation by a brief summary. Now let me talk about environmental problems and how spatial datasets can be used for environmental studies of Mongolia. Well, for environmental studies, the spatial information can play an important role, and such information can be collected from a number of sources, such as a field survey, planning maps, topographic maps, digital cartography, thematic maps, remote sensing, GIS, and GPS. Today, I will focus on mainly remote sensing, GIS, and GPS technologies. While in general, remote sensing can be defined as art, science, and technology of obtaining information about an object without any physical contact. And GIS can be defined as a spatial planning and decision-making tool. And meanwhile, GPS can be defined as a global navigation satellite system providing geolocation of the Earth's object. While in general, in this study, we wanted to demonstrate how spatial techniques based on remote sensing, GIS, and GPS can be used for environmental monitoring and management, and for the analysis, we used multi-source satellite images with different spectral and spatial resolutions, as well as different spatial data sets represented in different formats. And now let me talk about forest change study using multi-temporal Landsat and GIS data. Well, in the present study, we wanted to demonstrate how multi-temporal optical remote sensing and GIS datasets can be used for forest change study in Selanga IMAC. And for this study, we have selected Landsat images from 1990, 2010, and 2015. While we had 6 Landsat scenes, and at the beginning, we mosaiced all the satellite images, and here you can see the mosaiced Landsat images from 1990, 2010, and 15. And the applied techniques are histogram matching, georeferencing to a UTM projection, areas of selection method using a polygon-based approach, and historical GIS data, and Jeffreys Matsushita distance, maximum likelihood classification, followed by fuzzy convolution with a 5x size window. And here you can see the results of the classification, and using those classified images, one can see that what kind of forest changes had occurred in between 1990 and 2015. For instance, in 1990, forest occupied 29,791 square kilometers. Meanwhile, in 2015, the cover was decreased to 23,753 square kilometers. Now let me talk about our second case study entitled Posture Land Change Study Using Optical and SAR Images. Well, when we combine optical and SAR images, mainly we talk about multi-source data sets followed by processing and analysis, and that's why this case study can be called as a posture land change study using multi-source data sets. And well, actually we had on one hand optical data sets, SAR data sets, topographic and thematic maps of varying scales, and GPS measurements were used the location of the herders during winter and summer camps. And to demonstrate some of the data sets, I have shown here Landsat and pulsar images obtained in 2014. Well, if you look at the title, we say using advanced spatial techniques, and that's why we have to demonstrate and apply some of the advanced techniques used in spatial context. And for this purpose, here we invented advanced classification algorithm, and it uses spectral and the spatial thresholds defined from the local knowledge, and the contextual knowledge was defined on the basis of the spectral and textural variations of the land surface features on the color images. Meanwhile, spectral thresholds use the upper and lower limits of the spectral values of the training samples, etc. And here you can see the results of the northern trisomes of Arhangla Emak. Well, actually, as we conduct posture land change study using at this table, one can see what kind of changes had occurred in those zones in between 1987 and 2014. For instance, posture land occupied roughly 390,000 hectares of land in 1987. Meanwhile, degraded pasture land occupied only roughly 85,000 hectares in 1987. Then, in 2001, these two land cover classes occupied 381,000 and 180,000 hectares respectively. And when we evaluate pasture land changes using the latest data sets acquired in 2014, the pasture land was decreased to 275,000 hectares. Meanwhile, degraded pasture land was increased to 190,000 hectares. While looking at those results, people working in the fields of environment, land management, and agriculture can use these data sets for their analysis and other decision-making processes. Now let me talk about analysis of environmental conditions using multi-temporal interferometric SAR images. And as a test site, we selected Slenga River Basin located in northern Mongolia. And as data sources, we have ERS-12 tandem pass interferometric SAR images acquired in in October of 1997 and August of 1998, as well as pulsar images acquired in September of 2015. While initially we had single-look complex images. From those raw SAR data, we had to extract some amplitude and phase images. And during the interferometric processing, we obtained coherence images with different qualities. And coherence is a measure of variance or the phase difference of the imaged surface in the time between the two SAR data acquisitions. And coherence values range from 0 to 1. If coherence is close to 0, then, close to 0, then there are tremendous changes. If it's close to 1, almost no change, while actually in environmental areas we have so many environmental changes which are caused by different environmental factors. And in urban areas, definitely we will have very high coherence values because almost no environmental changes, etc. And looking at those coherence images from 1997, 1998, and 2015, one can observe what kind of environmental changes occurred during August, October, and September months in those years. Now let me talk about my last case study entitled Global Environment Monitoring Using Moderate Resolution Optical Remote Sensing Images. While in Mongolia, we have MODIS receiving station installed at the Environmental Information Center of the Ministry of Environment and Tourism, and data acquired from this MODIS station can be efficiently used global environmental monitoring throughout the country. And just I want to demonstrate some of the case studies conducted using MODIS images. And while as MODIS has 36 spectral bands in between blue and thermal infrared ranges, the data sets can be used for almost all kinds of environmental monitoring and management activities. For instance, you can see here MODIS images, What's the matter? Something wrong? Something wrong with this pointer. Well, for instance, you can see MODIS images indicating green vegetation condition starting from the beginning, mid, and end of June and the end of July. And looking at those NDVI images, environmental and agricultural decision makers can make different decision-making processes. For instance, what is good pasture, where to put their livestock, etc. And also MODIS images can be efficiently used for snow cover monitoring. And here you can see snow cover images in between January and April. For instance, January, February, March, and April. And you can see how the forest cover has been decreased from month to month. And also thermal bands of MODIS datasets can be efficiently used for forest and steppe fire monitoring in Mongolia. And for instance, here you can see MODIS image indicating forest and steppe fires occurring mostly in northern and eastern parts of the country. And also, at present, one of the global problems occurring in the Earth's surface, which is mainly originated from Mongolia, is yellow dust distribution. And short wavelength bands of the MODIS also can be efficiently used for yellow dust distribution throughout Mongolian and East Asian region. And you can see, for instance, MODIS image indicating yellow dust spread occurred in the spring period in Mongolia. Well, in such a way, at the regional level, we can use high resolution satellite images along with GPS and GIS datasets for efficient environmental monitoring and management. And at local level, definitely we would need very high resolution satellite images such as world view, ICONOS, etc. But I did not include those case studies in my presentation. And at a global level, definitely, not only we, the world, can efficiently use MODIS data sets for all kinds of environmental monitoring and management. Well, the overall idea of this research was to demonstrate how the advanced spatial techniques based on remote sensing, GIS, and GPS efficiently used for environmental monitoring and management, and we conclude that all of these techniques that I have just mentioned can be efficiently used for environmental monitoring and management, not only in Mongolia, but they can be used throughout the world. And that's the end of my presentation, and thank you very much for your attention.